Hey everyone, and welcome! Today, we're going to pull back the curtain on something you probably do 100 times a day without even thinking about it, loading a web page. It feels like total magic, right? But it's actually one of the most incredible systems ever engineered. So think about it. You click a link and bam, the page is just there. But what is actually happening in that split second? Well, your request is going on this unbelievable, high-speed journey across the globe, and that's exactly what we're going to map out today. From our point of view, it couldn't be any simpler. Step 1, we tell the browser where we want to go. Step 2, we're there. It feels totally seamless, like there's nothing in between. But that's the thing. Between those two simple steps lies this entire hidden journey. It's this lightning-fast process of translating, packaging, and navigating that happens completely behind the scenes. So let's peek behind that curtain. So how in the world does a global network with billions of devices, all made by different companies, all talking at once, how does it not just turn into complete and utter chaos? Well, it all comes down to a shared rulebook. Yeah, the internet isn't magic at all. It's a system that's built on one simple idea: agreement. All these different devices agree to talk to each other using a shared set of rules, and those rules are called protocols. Protocols are what makes sure that a message sent from, say, your phone is actually received and understood by a server halfway around the world. Now, to handle all this complexity, engineers came up with a really brilliant idea. You just break the problem down into smaller pieces, into layers. The original master plan for this whole concept has 7 of them, and each layer has exactly one job to do. And this master plan? It has a formal name, the OSI model, which stands for Open Systems Interconnection. It's really just a framework, a concept. Think of it less like a physical thing and more like an architect's blueprint that shows how all the different pieces are supposed to fit together so the whole building doesn't fall down. And this is where it gets really interesting, because here you can see the difference between the blueprint and the real world. On the left, you've got that 7-layer OSI model we just talked about. But on the right, you have the 4-layer TCP/IP model, which is what the internet actually runs on today. So why the difference? Well, TCP/IP was built right alongside the early internet. It was just simpler, it worked really well, and it became the standard. But it follows that exact same core idea as OSI: divide the problem to conquer it. Okay, so we've got these layers, but how do they actually, do anything with your request? It all comes down to how the message gets wrapped up and ready for its trip. And honestly, the best way to picture this is to think about sending mail. First, you write the letter, right? That's your actual data request, using a protocol called HTTP. Then you put that letter in a secure, trackable envelope to make sure it gets there in one piece. That's the job of TCP. Next, you write the address on the outside of the envelope. That's the IP address. And finally, you give it to the mail truck, which is a physical network of Wi-Fi signals and fiber optic cables to get it on its way. So as your request moves down through those layers, each layer adds its own little piece of information, its own header. This process of wrapping your data in more and more layers of instructions has an official name. It's called encapsulation. And what you end up with is this neat little nested digital package. See? Right at the very center is your actual request. That gets wrapped by TCP instructions for reliability, which then gets wrapped by IP information for addressing. This final all-wrapped-up unit is what we call a packet. And this is the thing that actually zooms across the internet. Kinda cool, right? Alright, so our packet is all wrapped up, it's encapsulated, it's ready to go, but where is it going? The internet is a ridiculously huge place. It needs a very specific address. And here is the next big puzzle we have to solve. We humans, we think in names, like Google.com. But computers, routers, all the machinery of the internet, they don't have a clue what that means. They speak in numbers, specifically IP addresses. So how on earth does your browser turn the name you typed into a number it can actually use? The answer is something called DNS, the Domain Name System. And it is, put simply, the internet's phone book. It's this massive global database, and its only job is to look up the human-friendly name you give it and spit back the machine-friendly IP address number. It is truly one of the unsung heroes of the web. And hey, this isn't just some abstract theory. You can actually see this happen on your own computer. If you use a simple command like nslookup, your computer literally asks the DNS system, hey, what's the number for google.com? And it gets back an address just like this one. That number That's the real destination for your data packet. Now, to get really specific, your device is actually juggling two different kinds of addresses. The IP address is its temporary spot on the internet. Think of it like your hotel room number. It can change, but the MAC address, that's its permanent burned-in serial number. It never changes. The internet uses the IP address to get your packet to the right building, and then the local network uses the MAC address to deliver it to the right room, to your exact device. Okay, we have gone pretty deep into the nuts and bolts of packets, layers, and addresses, but let's zoom out for a second. Why is this whole layered, rule-based system so incredibly important? What's the big picture? Well, this table really shows you the workhorses of the internet. Pretty much everything we do online, from browsing a site with HTTP to sending an email with SMTP, depends on one of these specific protocols. And check out those port numbers. If an IP address is like the street address of a giant apartment building, the port number is the specific apartment number. It tells the data exactly which application it's supposed to go to. Your browser, your mail app, whatever. So let's wrap this up with the key takeaways. First, all your data gets broken down into these little pieces called packets. Second, the entire journey is guided by a shared set of rules, these protocols, that are all organized in layers. Each layer has one job, whether it's addressing or making sure the data arrives safely. And all of it, working together, DNS, TCP, IP, is what makes sure your click turns into a web page, almost instantly. It's this beautiful layered system that lets this impossibly complex global network just work. You know, when you boil it all down, the entire system we've just walked through is built on two things: established rules, and maybe more importantly, trust. We trust that the rules will be followed. We trust that our data is going where it's supposed to go. And that kind of leaves us with a final big question to think about. In a world that's more connected every day, are we doing enough to protect that foundational trust?